Welcome, weary traveler, to Sleepy Wiki. Find a comfortable space, let your shoulders gently drop, and allow your breath to slowly deepen, settling into a rhythm of peace. Tonight, our quiet exploration leads us to a name whispered through time: Mariana. Imagine a presence that evokes both profound depth and gentle vastness. Is she the calm surface of a moonlit sea, reflecting ancient stars, or the silent, immense pressure of the deepest chasms, holding secrets beyond our imagining? We won't hurry for answers, but simply allow the gentle currents of curiosity to carry us on a journey not of hurried discovery, but of peaceful contemplation. Let the idea of Mariana settle softly in your mind, like dust motes dancing in a forgotten beam of light. If you find comfort in these quiet moments, perhaps a gentle tap on the like button or a soft subscription could help others drift to sleep with us too. So, let us now gently turn our attention and begin our quiet journey into the world of Mariana. Beyond the surface shimmers lies the very bedrock of our planet, where the story of the Mariana Trench truly begins. Imagine, if you will, our Earth not as a solid, unmoving sphere, but as a colossal, slow-motion puzzle. Its outermost shell, the lithosphere, is cracked into immense pieces like ancient, fractured pottery. These pieces, vast and ponderous, are called tectonic plates, and they are forever in motion, drifting, grinding, and colliding across the Earth's mantle, a journey measured not in heartbeats, but in eons. At the heart of the Mariana Trench's creation lies a grand geological ballet, a slow, inexorable dance between two of these monumental plates. Picture two enormous rafts floating upon a viscous, unseen sea. One of these rafts is the mighty Pacific Plate, a true titan among Earth's geological segments, encompassing much of the Pacific Ocean floor. The other, somewhat smaller but equally significant for our story, is the Philippine Sea Plate. It's at the boundary where these two giants meet that the breathtaking drama of the Mariana Trench unfolds. This isn't just any meeting. It's what geologists call a convergent plate boundary, a place where plates are driven together, destined to collide. But unlike two cars crashing, this collision is a graceful glacial yielding. One of these plates, out of a profound and ancient destiny, is compelled to dive beneath the other. This process, so fundamental to the shaping of our world, is known as subduction. Think of it like a vast, heavy blanket, slowly, majestically, slipping beneath the edge of a bed. The Pacific Plate, being older and therefore colder, has had more time to cool and contract. This makes it significantly denser than the younger, warmer crust of the Philippine Sea Plate. And in the silent, powerful physics of our planet, density dictates destiny. The heavier, denser Pacific Plate, burdened by its immense age and mass, yields to the irresistible pull of gravity. It bows, it bends, and then it begins its long, slow descent, plunging deep into the Earth's mantle beneath the Philippine Sea Plate. This colossal downward bend is precisely what forms the Mariana Trench. It's not a rift, not a tear in the conventional sense, but rather a profound, elongated depression in the ocean floor, a vast, curving valley carved by the relentless plunge of an entire oceanic plate. As the Pacific Plate begins its descent, it creates a monumental furrow, a colossal wrinkle in the Earth's crust. This is why the trench is not a sudden, sharp drop-off, but a gradual, albeit steep, slope leading down into unimaginable depths, stretching for over 2,550 kilometers, that's more than 1,500 miles, in an elegant crescent shape. The angle of this subduction is particularly steep in the Mariana region, a factor that contributes significantly to its extraordinary depth. The old, cold, and heavy Pacific Plate is not just slipping, it's practically free-falling into the mantle, pulled by its own immense weight in a phenomenon known as slab pull. This powerful gravitational tug accelerates its descent, deepening the trench further and further, making it the deepest known point on Earth's surface. And as one plate descends, its journey doesn't end there. Imagine the tremendous heat and pressure it encounters as it sinks hundreds of kilometers into the Earth's interior. This immense heat begins to melt parts of the descending Pacific Plate, transforming solid rock into molten magma. This molten rock, being less dense than the surrounding mantle, begins its own slow, arduous journey upwards, like a subterranean whisper rising from the abyss. When this magma eventually breaches the surface, usually along the overriding plate, it erupts, forming chains of volcanoes. And precisely parallel to the Mariana Trench, about 200 kilometers to the west, we find a perfect testament to this fiery consequence: the beautiful chain of the Mariana Islands, a volcanic arc born from the very same forces that sculpted the trench. These islands are literally the peaks of underwater volcanoes, their fiery breath a stark contrast to the cold, crushing darkness of the trench below, yet intricately linked by the ceaseless motion of our planet. So, the Mariana Trench is not merely a hole in the ground. It is a profound testament to the Earth's dynamic nature, a scar of unimaginable scale, carved by the slow, powerful embrace of two colossal tectonic plates. It's a place where the ocean floor itself bends and dives, beginning an epic journey back into the fiery heart of our world, a journey that has been ongoing for tens of millions of years. And in understanding this great geological origin, we begin to grasp not just its depth, but the incredible ancient forces that continue to shape our home even as we sleep. Now, with the majestic forces that forged the trench understood, let us ponder the incredible adaptations of life that have managed to thrive in its extreme environment, a story of resilience written in the deepest shadows. The majestic forces we've witnessed have sculpted something extraordinary, a shape, a form, a presence on the ocean floor that defies imagination. To perceive it, we need an extraordinary pair of eyes, not just for seeing light, but for understanding the ocean's profound depths through sound and pressure. For that is how we, as scientists and dreamers, have begun to map this colossal canyon. This process, known as bathymetry, is like painting a portrait of the invisible, using sound waves to sketch out the mountains and valleys hidden beneath the vast, dark waters. Picture a long, slender scar across the face of our planet's western Pacific floor, a magnificent crescent moon carved into the seabed. This is the Mariana Trench. It stretches for an astonishing 2,550 kilometers. That's roughly 1,180 miles. almost the distance from New York to Denver or from London to Moscow. But while its length is immense, its width is surprisingly modest, averaging only about 69 kilometers or 43 miles at the surface. Think of it as a vast, elongated V-shape, a colossal natural furrow that tapers down ever so gradually at first, then more steeply into an unimaginable abyss. This incredible shape, this geomorphology, is not accidental. It is the signature of one of Earth's most powerful, yet most graceful, geological dances. Subduction. Far, far beneath the waves, two colossal pieces of Earth's outer shell, called tectonic plates, meet. The mighty Pacific Plate, older and denser, gently but inexorably bows and slides like a vast, slow-motion conveyor belt beneath the lighter Mariana Plate. As it descends, it pulls the ocean floor with it, creating this profound depression, a testament to the immense patient power of our living planet. The trench is, in essence, the crumple zone, the meeting point where one part of the Earth's crust gracefully dives into the mantle below. As we trace this V-shape downward, the slopes become steeper, some areas plunging at angles that would make even the most seasoned mountaineer pause. These aren't sheer, polished walls, but rugged, intricate landscapes sculpted by seismic activity and the slow creep of rock. In places, researchers have found what appear to be natural terraces or benches, like colossal ancient steps leading further and further into the dark. These features hint at the complex geological history of the trench, perhaps marking different phases of faulting and uplift over millions of years. But within this grand, elongated canyon lies a specific spot that captures our imagination more than any other: the Challenger Deep. It's not a single pinpoint, but rather a small, almost bowl-shaped depression, an inner sanctum located towards the southern end of the Mariana Trench. Here, the ocean floor reaches its absolute nadir, the deepest known point in all of Earth's oceans. While precise measurements vary slightly with technology and methodology, the Challenger Deep plunges to approximately 10,984 meters, or roughly 36,037 feet below the surface. To truly grasp this depth, imagine taking the world's tallest mountain, Mount Everest, and inverting it. Its peak would still be more than a mile below the surface of the ocean at Challenger Deep. Consider the sheer scale. If you were flying in a commercial airliner at its typical cruising altitude of around 35,000 feet, you would still be above the deepest point of the Challenger Deep. This depth means that for every square inch, the pressure becomes almost unbearable. At the bottom of the Challenger Deep, the weight of the water above exerts over 1,000 times the atmospheric pressure we experience at sea level. It's like having nearly 50 jumbo jets resting on your head, or, perhaps more poetically, like holding up the weight of 1,000 elephants with your bare hands. Despite this immense pressure, the floor of the Challenger Deep isn't a perfectly flat, featureless plain. Modern bathymetric maps, painstakingly compiled from multi-beam sonar surveys, reveal a surprisingly complex topography even at these extreme depths. There are subtle ridges, small hills, and depressions, all smoothed over by eons of accumulated sediment, fine particles of clay, volcanic ash, and the microscopic remains of countless marine organisms that have drifted down from the sunlit world above, forming a perpetually soft, silty blanket. This slow, steady rain of particles, called marine snow, continues unabated, millennia after millennia, gradually softening the edges of the trench's raw geological forms. The journey down into this realm is not just a descent into pressure, but into an eternal night. Beyond the shallow, sunlit zone, the light rapidly fades, giving way to the aphotic zone, a world of perpetual darkness. Here, the only light comes from the occasional bioluminescent creature, or perhaps a flash from an exploring submersible. The temperature, too, plunges to near freezing, typically between 1 to 4 degrees Celsius, 34 to 39 degrees Fahrenheit, adding another layer of extreme conditions to this most isolated of environments. So, as we map this extraordinary world with sound, we begin to appreciate the grand design of our planet. The Mariana Trench is not just a hole in the ground, it is a dynamic, ever-changing feature, a testament to the raw, beautiful power of plate tectonics. It's a place where time moves differently, where geological processes unfold over millions of years, shaping an environment unlike anywhere else on Earth. And as we understand the colossal scale and the intricate architecture of this deep-sea canyon, our thoughts naturally turn to another question. What animates this vast cathedral of stone and sediment? The answer lies not in the mighty edifice itself, but in the very substance that fills it, the water. Imagine this incredible, liquid world stretching down, 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 mile after silent mile. It isn't a static, unmoving realm, but rather a place of profound, almost imperceptible motion, where the deepest currents whisper tales of distant shores and ancient cycles. At these crushing depths, the water is a unique entity. It's intensely cold, just a few degrees above freezing, perhaps 2 to 4 degrees Celsius. This chill comes from its long journey, often originating in the frigid polar regions of our planet. And under the immense pressure, where each square inch bears the weight of thousands of pounds of water, it becomes incredibly dense. It's as if the water molecules themselves are pressed closer together, creating a heavy, almost sluggish yet immensely powerful medium. Think of it like incredibly thick, liquid glass, moving with a ponderous, stately grace. This density is key to understanding the deep ocean. Water, like air, prefers to settle into layers based on its density. Colder, saltier, denser water sinks, while warmer, fresher, lighter water floats above. This creates a stratified ocean, a magnificent layered cake, where each stratum holds its own unique properties. In the abyssal plains and trenches, these layers are often subtle, but they are there, like invisible shelves that guide the flow of water. But how does water move in such a place, seemingly so cut off from the sunlit surface? This brings us to the grand, silent engine of our oceans, the geothermal circulation. Imagine a colossal, global conveyor belt winding through every ocean basin, driven by differences in temperature, thermo, and salinity, haline. It's a vast, slow-motion river that connects the world. In the polar regions, like the Arctic and Antarctic, surface waters become incredibly cold. As sea ice forms, it leaves behind its salt, making the remaining water even saltier and thus denser. This super-dense water, heavy with cold and salt, begins to sink. It descends, sometimes plunging thousands of meters, cascading down into the deep ocean like an invisible liquid waterfall. Once in the deep, this frigid, oxygen-rich water begins its long, meandering journey. It flows across the abyssal plains, through the valleys and trenches of the ocean floor, traveling for centuries. This deep current, often called the Great Ocean Conveyor Belt, creeps along at speeds that would barely register to our hurried surface sensibilities, perhaps only a few centimeters per second, or less than a mile a day. But its sheer volume is staggering, carrying more water than all the world's surface rivers combined. Think of it as the planet's vast, deep circulatory system, vital for distributing heat, nutrients, and precious oxygen throughout the global ocean. And even in the Mariana Trench, this immense global flow has an influence. While the trench itself is a deep, confined basin, it's not entirely isolated. The powerful abyssal currents, nudged by the Earth's rotation, a force known as the Coriolis effect, and steered by submarine topography, brush against and sometimes flow into its upper reaches. Imagine the trench walls acting like the banks of a river, guiding and channeling the movement of these ancient water masses. The Coriolis effect, though subtle, gently deflects these massive water movements, often causing them to curve right in the northern hemisphere and left in the southern, even thousands of meters down. Within the trench itself, local hydrodynamics become even more fascinating. The incredibly steep slopes and deep, narrow basin can create unique current patterns. Water might swirl in enormous slow-motion eddies or be funneled along the trench axis. These topographic features don't just guide currents, they can also create turbulence and mixing, stirring the profound depths in subtle ways. Picture these deep currents encountering a colossal underwater mountain range or the sheer face of the trench and being forced to rise, fall, or divert, creating localized whirls and quiet zones. And even here, at the planet's deepest point, the rhythmic pull of celestial bodies exerts its gentle power. Tidal forces, though diminished, still resonate through the vast water column. They manifest not as dramatic rising and falling surfaces, but as subtle internal waves, internal tides that travel along the density layers within the ocean. These are waves that break not on a shore, but against the hidden slopes of submarine mountains and the deep walls of the trench, gently rocking the water back and forth, contributing to the slow, continuous mixing of the deep. Think of these internal waves as ghostly ripples moving through the water column, often unseen and unfelt at the surface, but profoundly important for distributing energy and momentum at depth. They are a critical mechanism for bringing nutrients and oxygen from different layers together, like a quiet internal breath of the ocean. This continuous, albeit slow, movement of water is what keeps the abyssal ecosystem alive. Without these currents, without the thermohaline circulation bringing cold, oxygen-rich water from the surface, the deepest parts of the ocean would become stagnant, lifeless pools. The currents act as an invisible delivery system, bringing the necessities for life, however sparse, to these extreme environments. The hydrodynamics of the abyssal zone are a testament to the ocean's interconnectedness and its profound, patient power. It is a world of constant motion, where every drop of water is on an epic journey, influenced by forces both global and local, visible and unseen. Yet within these flowing rivers of the deep, a profound shift in the very fabric of existence asserts itself. It's not just the darkness, nor the chilling cold, but something far more immense, far more encompassing: pressure. Imagine, if you will, the gentle weight of the air above you right now, a familiar comfort we barely notice. Down here, in the abyssal plains and the trench's deepest creases, that weight multiplies beyond comprehension. It's like having an entire column of the ocean, miles high, pressing down on every inch of your being. To put it into a more tangible image, it's akin to having the full weight of 50 jumbo jets balanced on your thumbnail, or more simply, about 1,000 times the atmospheric pressure we experience on the surface. This isn't just an abstract number. It's a relentless force that seeks to compress, to flatten, to fundamentally alter the very chemistry of life. Think of the intricate, delicate molecular machinery that makes up every cell in your body. The proteins, those tireless molecular workers, each folded into a precise, three-dimensional shape, essential for its function. Under such extreme pressure, these proteins would buckle and unravel, like an intricately folded paper crane squashed flat. They would lose their delicate form, cease their vital work, and life as we know it would simply cease. Cell membranes, the flexible skins that enclose our cellular world, would stiffen and lose their essential fluidity, unable to regulate the flow of molecules in and out. Any gas-filled spaces, like the swim bladders many fish use for buoyancy, would be instantly crushed into non-existence. It is a world designed to crush life as we understand it, yet life not only persists here but flourishes, evolving astonishing solutions to these monumental challenges. The creatures of the Mariana Trench are not merely surviving, they are masters of this high-pressure realm, their bodies exquisitely tuned to a world that would obliterate ours. They are often called pisophiles or barophiles, pressure lovers, and their existence is a testament to life's profound adaptability. One of the most remarkable adaptations is found deep within their very chemistry, a subtle molecular shield woven into their cells. Imagine a microscopic bodyguard standing watch over the delicate proteins, ensuring they retain their perfect functional shape even under the most extreme squeeze. This bodyguard is often a small organic molecule called trimethylamine N-oxide, or TMAO for short. TMAO acts as a counter-osmolyte, meaning it works to stabilize proteins and prevent them from denaturing under pressure. It essentially helps the proteins hold on to their vital water molecules, preventing them from being squeezed out, a process that would otherwise distort their structure and render them useless. The deeper the organism lives, the higher the concentration of TMAO found in its cells. A clear indicator of its critical role in survival. It's like adding internal scaffolding that becomes stronger and more pervasive the greater the weight it must bear. Beyond this internal shield, the very architecture of their cells has been redesigned. Their cell membranes, those crucial boundaries, are often composed of a higher proportion of unsaturated fatty acids. Picture the difference between a stiff, solid block of butter and a pourable olive oil. Unsaturated fatty acids introduce bends and kinks into the lipid molecules, preventing them from packing together too tightly. This keeps the membranes fluid and flexible, even under immense pressure that would otherwise turn them rigid and brittle. These flexible walls allow cells to maintain their function, allowing molecules to pass through and cellular processes to continue unhindered, like a highly adaptive liquid armor. And what of the proteins themselves, the very engines of life? They too have undergone evolutionary refinement. Deep-sea organisms possess specialized proteins and enzymes that are inherently more pressure-resistant. Their molecular architecture is subtly different, less prone to buckling, designed to maintain stability and function optimally under conditions that would render our own proteins inert. It's as if their precision instruments have been redesigned from the ground up, not just to withstand the pressure, but to thrive in it, performing their intricate tasks with unwavering efficiency. Perhaps one of the most visually striking adaptations, though, is in the very structure of their bodies. You won't find deep-sea trench creatures with large gas-filled swim bladders. Such a feature would be a fatal vulnerability, instantly crushed. Instead, many of these organisms, like the ethereal Mariana snailfish, possess soft, gelatinous bodies. Imagine a living jelly yielding to the pressure rather than resisting it. Their skeletons, where they exist, are often cartilaginous rather than bony and dense, further reducing their overall density and making them less susceptible to compression. This approach minimizes air pockets and maximizes the internal pressure of their bodies to be nearly equal to the external pressure, effectively making them invisible to the crushing force. Their physical form, delicate in appearance, is actually an engineering marvel, designed for effortless existence in a world of profound squeeze. Life here also moves at a different rhythm. The extreme cold, coupled with the scarcity of food, means that metabolism is often incredibly slow. Creatures grow slowly, mature slowly, and can live for astonishingly long periods. It's a life lived in slow motion, a deliberate waltz through the eternal twilight. This slow pace is another adaptation, conserving energy in an environment where resources are precious and hard-won. Some deep-sea species even exhibit deep-sea gigantism, growing much larger than their shallow water relatives, a phenomenon thought to be linked to this slow metabolism, long lifespans, and reduced predation pressure. From the unseen molecular shields of TMAO to the yielding gelatinous forms that embrace the pressure, the inhabitants of the Mariana Trench have truly mastered their extreme environment. They are living whispers of resilience, showing us that even in the most inhospitable corners of our planet, life finds a way to not just exist, but to endure and even thrive, continually surprising us with its ingenuity. As we gently reflect on these incredible feats of adaptation, these unique solutions to a world of crushing pressure, another profound mystery beckons. How does life find sustenance in a world of perpetual darkness, where the sun's light never reaches? The answer reveals an alien world right here on our own planet. A realm utterly devoid of sunlight, where the chill of the crushing ocean would seem to forbid all life. We drift deeper now, past the last faint whispers of the sun's reach, into the perpetual midnight of the abyssal plain, a place that stretches for untold miles across the ocean floor. And then, as if by some impossible magic, a shimmering oasis appears in the darkness. Pillars of rock rise like ancient smokestacks, not breathing fire, but exhaling clouds of dark, mineral-rich fluid into the surrounding frigid water. These are the hydrothermal vents, and they are the vibrant, throbbing hearts of some of Earth's most extraordinary ecosystems. For centuries, we believed that all life on Earth ultimately depended on the sun, that photosynthesis, the conversion of light into energy, was the universal foundation of the food web. But these deep-sea oases revealed a revolutionary truth. Life doesn't always need sunlight. In the profound depths of the Mariana Trench and its surrounding volcanic arcs, where the pressure is immense and sunlight is but a distant memory, a different kind of alchemy takes place, an ancient process called chemosynthesis. Picture these vents, some standing dozens of meters tall, like towering spires forged from the very minerals they spew. They are often called black smokers or white smokers, depending on the chemicals they release. Black smokers erupt with superheated water, reaching temperatures of over 400 degrees Celsius, laden with a cocktail of dissolved metals like iron and manganese, and crucially, hydrogen sulfide. This toxic gas, which smells like rotten eggs on land, is the lifeblood of these deep-sea communities. White smokers, a bit cooler, release lighter-colored minerals, often rich in barium, calcium, and silicon. But how do these incredible structures form? The answer lies deep within the Earth's crust, in the fiery dance of tectonic plates. In areas where the Earth's crust is thin or spreading apart, like the Mariana Trough adjacent to the trench, seawater seeps down into cracks and fissures in the sea floor. As it penetrates deeper, it gets superheated by magma and reacts with the hot rocks, picking up minerals and chemicals. This chemically altered superheated water then rises back to the surface through vent chimneys, creating those surreal plumes of smoke. It's like the Earth itself is breathing, exhaling the very essence of its molten heart. This exhalation is the feast. Instead of plants capturing sunlight, specialized microorganisms, bacteria and archaea, perform chemosynthesis. They are the primary producers here, just as plants are on land. These tiny microscopic alchemists don't need light. Instead, they oxidize inorganic compounds like hydrogen sulfide, methane, or even iron, transforming their chemical energy into organic matter, the very building blocks of life. Think of it as a cosmic kitchen where the geothermal heat is the stove, and the chemicals from the vents are the ingredients, all cooked up by microbial chefs. And around these vibrant hot springs in the abyss, life flourishes in astonishing abundance. Imagine fields of giant tube worms, some reaching over 2 meters in length, swaying gently in the currents. These magnificent creatures, unique to these ecosystems, have no mouth, no gut, and no anus. How do they eat? They host billions of those chemosynthetic bacteria within specialized tissues inside their bodies. It's a profound symbiosis. The worms provide the bacteria with a safe home and a steady supply of hydrogen sulfide and oxygen from the vent fluids, and in return, the bacteria produce all the organic nutrients the worms need. It's a biological partnership so deep it redefines what it means to be an organism. Alongside the tube worms, you'll find vast beds of giant clams and mussels, their shells often encrusted with strange, colorful minerals. Like the tube worms, many of these bivalves also house chemosynthetic bacteria in their gills, thriving on the chemical bounty. There are pale, ghost-like shrimp, blind crabs, and even bizarre fish, all adapted to this extreme environment of scalding hot water next to freezing cold, immense pressure, and a unique chemical diet. These organisms are known as extremophiles, lovers of extremes, and they represent some of the most resilient life forms on our planet. Within the Mariana Trench system itself, specifically in areas like the Mariana Trough and even in the Challenger Deep, scientists have discovered various types of vents. Some of these are serpentinite vents, which are especially fascinating. Unlike the more common basalt-hosted vents that primarily release hydrogen sulfide, serpentinite vents produce methane and hydrogen from different geological reactions. This means the chemosynthetic bacteria living around them specialize in consuming these different chemical compounds, supporting distinct, though equally vibrant, communities. These discoveries highlight the incredible diversity of life's strategies for harnessing energy, even within the same extreme environment. These ecosystems are dynamic, always changing. Vents can form and die out over time as tectonic plates shift and volcanic activity waxes and wanes. When a vent goes dormant, the life around it, dependent on its chemical output, eventually fades. But the larvae and spores of these organisms can drift through the deep ocean, sometimes for hundreds or even thousands of miles, searching for new active vents, new oases in the vast, dark desert of the deep sea. It's a constant cycle of death and rebirth, a testament to life's persistent drive to find a way. The discovery of these chemosynthetic worlds fundamentally changed our understanding of life's potential, expanding the boundaries of where we might find it, perhaps even beyond Earth. They are vibrant, bustling cities built upon chemical energy, proving that life is far more resourceful and adaptable than we ever dared to imagine. Yet how did we come to witness these wonders with our own eyes? But the Mariana Trench holds more secrets than just these fiery chemical gardens. Sometimes life finds a way to thrive in environments that seem utterly barren, far from the warmth and bounty of any vent, sustained by an entirely different kind of resilience. As we continue our journey, let's explore how life clings to existence on the vast, silent plains between these geothermal hearths, where the only sustenance seems to come from above, falling ever so slowly from the sunlit world far, far away. The answer lies in the remarkable ingenuity of the human spirit, our persistent drive to reach the unreachable. Imagine, if you will, standing at the edge of a cliff so vast it makes the Grand Canyon seem like a mere dimple in the earth. Now imagine this cliff plunging downward not into air but into an abyss of crushing water, endless night, and chilling cold. This is the realm of the Challenger Deep, the deepest known point in the Mariana Trench, a place where the weight of the ocean above could flatten a steel beam as if it were paper. For centuries, this colossal chasm remained utterly beyond our reach, a silent, mysterious sentinel at the very bottom of our world. The pressure there is an almost unfathomable force, reaching over 1,000 times the atmospheric pressure you feel at sea level. To put that into perspective, it's like having 50 jumbo jets stacked on top of a single human thumb. The sheer scale of this invisible weight is what makes the deep ocean, and particularly the Mariana Trench, such an extraordinary frontier for human exploration. Yet, the human heart holds a restless curiosity, a yearning to peer into every hidden corner of our planet, even those that seem designed to repel us. This yearning gave birth to an incredible lineage of machines, the submersibles. These are not like the graceful gliding submarines that traverse the shallower seas. Deep-sea submersibles are more akin to tiny armored cocoons built to defy the unimaginable forces that reign in the abyss. Their creation is a testament to the meticulous dance between science, engineering, and sheer audacity. The core challenge, of course, is pressure. To withstand it, these vessels must be encased in extraordinarily strong pressure hulls, often spherical in shape, a design known for its remarkable ability to distribute external forces evenly. Early pioneers, like the bathyscaphe Trieste, which made history's first manned descent into the Challenger Deep in 1960, utilized a thick, spherical cabin made of high-strength steel. This sphere, only about 6.5 feet in diameter, was the precious bubble that protected Swiss oceanographer Jacques Piccard and U.S. Navy Lieutenant Don Walsh from the ocean's crushing embrace. But a pressure hull alone isn't enough. How do you descend into such depths? And more importantly, how do you ascend? The Trieste employed a brilliant yet simple system. It was essentially an underwater blimp. Its main flotation tank, a massive hull above the cruise sphere, was filled with gasoline. Gasoline, being lighter than water, provided the necessary buoyancy. To descend, seawater was pumped into ballast tanks, increasing the overall weight. To ascend, hundreds of tons of iron shot, held in place by electromagnets, were simply released. The subsequent lightening of the vessel allowed the gasoline's buoyancy to lift it gently back to the surface. It was a marvel of elegant engineering, proving that humans could indeed visit the deepest place on Earth and return. And over the decades, submersible technology evolved. While the Trieste was a single-purpose vessel for an extreme dive, others like the iconic Alvin, launched in 1964, became the workhorses of deep-sea science. Alvin is famous for its role in exploring hydrothermal vents and even finding a lost hydrogen bomb, but it's built for sustained scientific work at depths up to 4,500 meters, not the extreme pressures of the Mariana Trench. Its titanium pressure sphere, though smaller than Trieste's, offers incredible strength for its operational range, protecting its 3 occupants. The continued quest for the very bottom, however, required new leaps. The modern deep ocean submersibles like Japan's Shinkai 6500 or China's Jiaolong represent the pinnacle of current manned submersible technology. These vessels are built with incredibly robust titanium alloys for their pressure hulls and often use syntactic foam, a specialized composite material made of microscopic glass spheres suspended in resin for buoyancy. This foam is incredibly strong, yet lightweight, replacing the need for massive gasoline tanks and allowing for more compact designs that can withstand phenomenal pressures. But it's not just about the hull. The deep is a realm of absolute darkness, save for the fleeting bioluminescence of its inhabitants. Powerful external lights, shining like brilliant stars, are essential to illuminate the alien landscape. Cameras, designed to function under extreme pressure, capture images that are beamed back to the surface, offering humanity a glimpse into this hidden world. Robotic arms, incredibly dexterous and strong, are used to collect samples, deploy instruments, and interact with an environment utterly hostile to human touch. The journey itself inside these metallic capsules is a profound experience. Imagine the slow, silent descent, watching the last vestiges of sunlight fade, giving way to an eternal twilight, and then to total, inky blackness. The temperature inside the sphere is carefully controlled, a tiny pocket of warmth against the surrounding near-freezing water. Life support systems tirelessly scrub carbon dioxide and replenish oxygen, making this tiny, isolated bubble a habitable space in the most uninhabitable of environments. Communication back to the surface is often through acoustic signals, as radio waves cannot penetrate water effectively, creating a ghostly, muffled exchange across miles of ocean. Whilst one of the most recent and technologically advanced expeditions to the Challenger Deep was undertaken by filmmaker and explorer James Cameron in 2012. His submersible, the Deep Sea Challenger, was a truly unique design. Instead of a traditional spherical hull for the pilot, it featured a long, slender, vertically oriented pressure sphere made of incredibly thick steel. This allowed him to descend quickly, and its unique shape provided an unparalleled view through a large acrylic viewport, offering a window into a world never before seen through human eyes at such depths. He was the first solo human to reach the Challenger Deep, a feat that pushed the boundaries of both human endurance and engineering. The development of these submersibles is not just about reaching a destination. It's about pushing the very limits of material science, robotics, and human endurance. Each dive is a carefully orchestrated ballet of planning, precision, and immense courage. The information gathered from these brief forays into the deep provides invaluable data about our planet's geology, its chemical processes, and the astonishing forms of life that have adapted to thrive in such extreme conditions. And as these brave vessels continue their silent voyages, piercing the veil of the deep, they unveil a world far richer and more complex than we ever imagined, a world of discovery that continues to unfold with each passing year. What have these voyages revealed? A vast liquid canvas, stretching beyond the reach of sunlight, into depths so profound they humble the tallest mountains on our planet. This is the realm we've been exploring, the Mariana Trench, a silent, ancient corner of Earth that guards its secrets with a formidable embrace of pressure and perpetual night. To truly appreciate the marvel of discovery here, we must first understand the sheer scale of this challenge. At its deepest point, the Challenger Deep, the weight of the water above is staggering. Over 1,000 times the atmospheric pressure we experience at sea level. It's like having 50 jumbo jets stacked on top of you, or the collective weight of millions of kilograms pressing down on every single square centimeter. It's a force so immense it would crush most conventional submarines and obliterate nearly every form of life we know. For so long it was a place of whispered myths, a blank space on our maps, almost as unknown as the surface of Mars. The very thought of life thriving here seemed impossible, a defiance of all natural laws we understood. Yet, the relentless curiosity of humanity, a quiet beacon in the vast darkness of the unknown, began its slow, deliberate work, crafting tools and developing courage to pierce through this seemingly impenetrable veil. Our earliest glimpses were like fleeting dreams, whispers carried back from an alien world. When the bathyscaphe Trieste, a vessel of brave human ingenuity, first descended into the Challenger Deep in 1960, It was a moment that redefined our understanding of what was possible. It was more than just a brave toe dip into an unknown ocean. It was a profound declaration that life might indeed exist in the most extreme places. The fleeting observation of a flat fish-like creature, a momentary shadow in the abyss, was enough to ignite the spark of possibility, proving that this dark world was not desolate. Decades later, with eyes and hands growing ever more sophisticated, our exploration truly began to blossom. Robotic submersibles, like silent deep-sea ballet dancers, began their slow, deliberate descent. These intrepid explorers, immune to the crushing weight that would instantly flatten us, carried our curiosity like a precious cargo. They mapped the contours of the abyss, gathered samples, and peered into the darkness with powerful lights, revealing sights that once belonged only to our wildest imaginings. What they found began to paint a breathtaking tapestry of adaptation and resilience, a vibrant testament to life's profound ability to find a way. Picture creatures born of twilight and immense force. The Mariana snailfish, for instance, is a marvel of soft, gelatinous resilience. It glides through waters that hover just above freezing, enduring pressures equivalent to 1/600 elephants balanced on a single thumbnail, a mind-boggling force that would instantaneously collapse any creature not specifically designed for it. Its body, almost entirely boneless, has evolved unique protein structures and a specialized kind of antifreeze within its cells, allowing it to maintain its cellular integrity and metabolic functions where others would simply rupture or crystallize. It's as if nature designed it specifically for this extreme embrace, a living whisper of what is possible when life adapts to the most challenging conditions imaginable. Then there are the amphipods, tiny crustacean scavengers like the delicate cleanup crew of this deep, dark world. Some species are found only here, their bodies laden with a special gel-like substance that helps protect their cells from the crushing pressure, transforming them into living pressure vessels, perfectly suited for their role. They dance in the eternal night, drawn to the infrequent gifts of food that drift down from the sunlit world above, showcasing an ecosystem that meticulously recycles every available nutrient. But the most profound discovery perhaps lies in the microscopic realm, the unseen architects of life that form the foundation of this deep ecosystem. Beneath the visible creatures thrives a hidden kingdom of microbes, bacteria and archaea. These tiny pioneers don't need the sun's warmth or light, which has never touched their world. Instead, they perform a kind of ancient alchemy called chemosynthesis, drawing energy from chemicals, like hydrogen sulfide and methane, released from the Earth's crust itself. It's a fundamental shift in perspective, akin to finding life on a different planet, for it reveals a completely independent energetic foundation for life, challenging our sun-centric view of biology and expanding our understanding of where and how life can emerge and persist. These microbial communities thrive in places like hydrothermal vents, underwater geysers that spew superheated mineral-rich water, creating vibrant oases in the desolate deep, or in cold seeps, where methane and other hydrocarbons bubble up from the seabed, sustaining entire ecosystems in the absence of sunlight. Each discovery is like finding a new intricate mechanism within a vast cosmic clock, showing us how our planet truly works, from its fiery core to its watery depths. The research frontier here is not just about cataloging new species, it's about understanding the very principles of survival. Scientists are poring over the genetic codes of these extremophiles, looking for the secrets locked within their DNA. How do their enzymes function under such stress? How do their cell membranes maintain their integrity? These questions aren't just for curiosity's sake. They hold keys to understanding life's resilience, its potential to exist in environments we once deemed utterly hostile, perhaps even on distant moons like Europa or Enceladus, where similar deep, dark, watery worlds might harbor their own mysteries. The Mariana Trench serves as a natural laboratory, offering profound insights into the astrobiological potential of other worlds. Our technology is advancing with breathtaking speed, making what was once impossible now routine. Autonomous underwater vehicles, or AUVs, are like silent, tireless sentinels, mapping the trench floor with sonar, taking samples, and capturing images with ever-increasing clarity, bringing back high-resolution portraits of the abyss. Remotely operated vehicles, ROVs, with their dexterous robotic arms, can collect fragile specimens and conduct delicate experiments, bringing the human touch without the human vulnerability. These machines are our extensions, our eyes and hands in a world where we cannot physically go, constantly pushing the boundaries of what we can observe and comprehend. The Mariana Trench is also a geological marvel, a dynamic scar on the Earth's face where one tectonic plate is diving beneath another in a process called subduction. This immense geological ballet shapes the very trench itself, creating earthquake zones and influencing the deep carbon cycle, how carbon moves from the Earth's surface into its interior, a process vital for regulating our planet's climate over geological timescales. Research here helps us understand Earth's internal rhythm, its slow, powerful breath, providing crucial data for global climate models and seismic hazard assessments. Yet, even in this pristine, untouched seeming abyss, human impact has begun to whisper its presence. A startling discovery revealed microplastics, tiny fragments of our discarded world, within the guts of amphipods living in the deepest parts of the trench. It's a sobering reminder that our actions ripple outwards, reaching even into the most remote and extreme corners of our shared planet, urging us to understand and protect this vulnerable deep-sea ecosystem before it's too late. It reveals the urgent need for a more sustainable relationship with our planet, even in its most distant frontiers. Every dive, every sample, every quiet observation from a remotely operated camera adds another brushstroke to this unfolding masterpiece of scientific understanding. The Mariana Trench is no longer just a dark, empty void. It is a vibrant, living laboratory, a testament to life's extraordinary tenacity, and a profound source of knowledge about Earth's past, present, and perhaps even the potential for life beyond our world. Yet beneath all these discoveries, beneath the creatures and the chemistry, lies something even more fundamental: the raw planetary forces that built this cathedral of the deep. Looking down upon our vast blue planet from a quiet perch among the stars, what might seem like an unchanging, serene marble is, beneath its swirling clouds and shimmering oceans, a world of ceaseless, monumental movement. Nowhere is this hidden ballet more profound, more powerful, than in the abyssal depths we've been exploring near the Mariana Trench. Here, in the profound silence of the ocean floor, forces that shape continents and sculpt mountains are constantly at work, unseen by human eyes, unheard by human ears, yet echoing through the very fabric of the Earth itself. These are the geophysical forces, the planet's own slow, ancient heartbeat, manifesting most dramatically as seismic activity. Now, Earth isn't a solid, static sphere, but rather a grand jigsaw puzzle, its surface cracked into enormous pieces we call tectonic plates. These colossal rafts of rock are not anchored in place. They're forever drifting, propelled by currents of molten rock deep within the planet's mantle, like silent ships on a sea of syrup. Near the Mariana Trench, two of these titanic plates meet in a slow, irresistible embrace. On one side, we have the immense Pacific Plate, one of the largest and oldest on our planet. Imagine it as a vast ancient carpet, slowly, inexorably sliding towards an edge. On the other side, patiently waiting, is the smaller, overriding Philippine Sea Plate, a silent sentinel. And what happens when these two titans converge? The Pacific Plate, being denser and older, bows gracefully, like a weary giant sinking onto one knee, and begins its long, slow descent beneath the Philippine Sea Plate. This incredible process, this planetary bow, is what scientists call subduction. Think of it like an enormous cosmic conveyor belt, slowly carrying a section of the Earth's crust back into its fiery heart. This is not a quick plunge, but a journey measured in millions of years, an incredibly slow, majestic glide into the unknown. As the Pacific Plate dives, it carves out that profound scar we know as the Mariana Trench, the deepest incision on our planet's surface, a direct consequence of this geological submission. Now, this isn't a smooth, frictionless descent. Imagine two immense, jagged surfaces grinding past each other, one diving beneath the other. The immense pressure, the sheer weight of continents, the friction between these colossal plates builds up over centuries, millennia. Sometimes, the plates get stuck. They lock together, holding their breath, resisting the relentless push from below. Yet the forces propelling them onward do not cease. The stress accumulates, like a giant, unseen spring being wound tighter and tighter. And then, inevitably, comes the moment of release. The rock can no longer bear the strain. It ruptures. It slips. It suddenly moves past its impediment. This sudden violent lurch, this planetary sigh of relief, sends vibrations rippling through the Earth's crust in all directions. These are earthquakes. In the Mariana region, earthquakes are a constant chorus, a testament to the planet's dynamic nature. They can be shallow, occurring near the surface where the plates first meet, manifesting as powerful tremors that can shake islands. But they can also be incredibly deep, reaching hundreds of kilometers into the Earth's mantle as parts of the subducting Pacific Plate break and fracture on their long journey downward. These are known as deep focus earthquakes, a mysterious echo from the Earth's hidden interior. Each tremor, each rumble, is a whisper of the colossal energies at play, a momentary redistribution of unimaginable stress. It's the planet adjusting, stretching, breathing. But the story doesn't end with subduction and earthquakes. As the Pacific Plate descends, it carries with it not just rock, but also water trapped within the minerals of the oceanic crust. As it plunges deeper into hotter regions, this water is driven out, like steam escaping from a kettle. This water then rises into the overlying mantle rock, surrounding the subducting plate. And here's where it gets truly fascinating. This water acts like a catalyst, lowering the melting point of the mantle rock. Imagine a thick, unyielding block of ice, and then imagine adding a tiny bit of salt to it. It begins to melt sooner, doesn't it? Something similar happens deep beneath the ocean floor. As the mantle rock begins to melt, it forms pockets of molten rock, or magma. This magma, being less dense than the surrounding solid rock, begins an incredible ascent. It slowly, painstakingly, rises through the cracks and fissures in the overriding Philippine Sea Plate, driven by buoyancy, like a hot air balloon seeking the sky. Where this magma eventually breaches the ocean floor, it erupts, forming underwater volcanoes. And along the eastern edge of the Philippine Sea Plate, parallel to the Mariana Trench, these eruptions have built a magnificent chain, the Mariana Volcanic Arc. Imagine a string of fiery pearls, hidden beneath miles of dark water, each one a testament to the subducting plate below. These aren't just isolated peaks, they are vibrant, active mountains, constantly growing, sometimes quietly seeping lava, sometimes erupting with explosive force, adding new rock to the Earth's crust, inch by slow inch. And from these volcanic foundations, another wonder emerges: hydrothermal vents. Imagine cracks in the seafloor, superheated by the magma below. Seawater seeps into these cracks, gets superheated to hundreds of degrees Celsius, dissolving minerals from the surrounding rock. This scalding, mineral-rich water then blasts back out into the icy cold ocean, forming towering chimneys of metallic sulfides and other exotic minerals. These vents, often called black smokers or white smokers, depending on the minerals they carry, are vivid proof of the Earth's inner heat reaching out to the surface. They are not just geological marvels. They are oases of life, supporting unique ecosystems entirely independent of sunlight, drawing their energy from the very chemistry of the Earth itself. It's a profound cycle where the planet's deep, fiery breath gives rise to life in the perpetual night. So, beneath the tranquil surface of the Pacific, near the Mariana Trench, the Earth is engaged in a perpetual silent drama. Plates grind, mountains rise, volcanoes breathe, and the very ground trembles. It's a slow-motion ballet where geological forces move with a patience that transcends human comprehension. The Pacific Plate continues its relentless plunge, carrying with it the secrets of ancient oceans, returning to the mantle from whence it came, fueling the fiery heart of our world. The earthquakes are the planet's momentary shudders, the volcanoes its fiery exhalations, and the hydrothermal vents its whispers of profound chemical creation. These are the geophysical forces, ceaselessly reshaping our world, reminding us that even in the deepest, most remote corners, our planet is alive, dynamic, and endlessly fascinating. And as these mighty forces sculpt the very bedrock of our world, they also create the unique environments where extraordinary life finds a way to thrive, adapting to pressures and temperatures unimaginable to us. Yet this realm, so far removed it feels like another planet, is not beyond our reach or our impact. Even here, in the profound stillness of the Mariana Trench, the whisper of our presence, the echo of human activity, can sometimes be found. It's a paradox, isn't it, that a place so ancient, so isolated, could bear the mark of creatures who dwell on the sunlit surface world thousands of meters above. Imagine, if you will, the vast shimmering surface of the ocean, a world of sunbeams and waves. On this bustling stage, we humans create and consume, build and discard. Sometimes what we discard, those everyday objects, those pieces of plastic, those forgotten fragments, begin an extraordinary and unintended journey. They drift on ocean currents, catching rides with the ebb and flow, sometimes for years. And then, slowly, inexorably, some of these fragments become heavy enough, waterlogged enough, to begin their descent. It's like tiny, unwanted snowflakes drifting downwards through miles of water, past schools of shimmering fish, past the silent migration of whales, down into the eternal twilight, and then into the perpetual night. These pieces, large and small, eventually settle on the abyssal plains, or get caught in the trench's formidable embrace. Scientists, with their curious robotic eyes, have discovered plastic bags at depths exceeding 10,000 meters, bottles nestled amongst ancient rocks. But even more subtly, more intimately, our plastic footprint manifests as microplastics. These are the tiny, almost invisible fragments, born from the slow breakdown of larger items, like dust motes, but far more enduring. They are so minuscule, so pervasive, that they can be mistaken for food by the creatures who dwell in the deep. Researchers have found these microscopic invaders within the bodies of crustaceans, like the small, unassuming amphipods that thrive in the crushing pressures of the Challenger Deep. Imagine these creatures, who have adapted over eons to survive in one of Earth's most extreme environments, now encountering materials utterly foreign to their ancient world, particles that offer no nourishment yet fill their tiny digestive systems. It's a stark reminder of how interconnected our planet truly is, how even our seemingly insignificant actions can reverberate through the silent depths. But plastics aren't the only guests unwelcome in this deep sanctuary. There are also invisible guests, ghosts of our industrial past, persistent organic pollutants, or POPs. These are chemical compounds, like polychlorinated biphenyls, PCBs, once widely used in industry, now banned in many parts of the world due to their toxicity. Yet, like restless spirits, they linger. They travel through the food chain, accumulating in the fats of animals. When these animals die, or when their waste settles, these chemicals slowly descend. Scientists have discovered alarmingly high concentrations of these PCBs in the very same amphipods in the Mariana Trench, levels comparable to those found in organisms living in some of the most polluted rivers and coastal areas on Earth. This phenomenon, known as biomagnification, means that as these chemicals move up the food web, from tiny organisms to slightly larger ones, their concentration intensifies, creating a toxic burden on creatures that have never seen the light of day. It paints a picture of a deep ocean that, despite its isolation, acts as a global sink, accumulating the residues of human activity from continents away. Beyond these direct physical and chemical imprints, the Mariana Trench and its surrounding ocean face broader, more diffuse challenges emanating from the cumulative force of our collective existence. Climate change, for instance, isn't just about rising temperatures at the surface. It subtly alters the entire oceanic system. The ocean absorbs a tremendous amount of carbon dioxide from our atmosphere, leading to ocean acidification, a slow, creeping change in the water's chemistry that could eventually impact deep-sea ecosystems, especially those relying on calcium carbonate for shells or structures. While the deepest parts of the trench are somewhat buffered from immediate surface changes, the entire food web, from the sunlight zone down to the abyss, is ultimately intertwined. And then, there's the shadow of future impacts. The vast mineral resources believed to lie on the deep-sea floor, in areas less extreme than the trench itself, but still part of the deep ocean, are increasingly eyed for potential deep-sea mining. While the Mariana Trench Marine National Monument offers protection, the broader deep ocean faces the possibility of industrial-scale extraction, which could disrupt fragile ecosystems, stir up sediments, and create noise pollution on an unprecedented scale. These are whispers on the horizon, but whispers that remind us of the immense power we wield and the profound responsibility that comes with it. But our story here isn't solely one of impact. It is also one of awakening and aspiration. The very act of discovering these human imprints has stirred a powerful current of conservation. Recognizing the unparalleled scientific and ecological value of this extraordinary region, the United States established the Mariana Trench Marine National Monument. This designation acts as a protective shield, safeguarding vast stretches of the trench, including the Challenger Deep, from activities like fishing, waste dumping, and mineral extraction. It's a testament to the idea that some places are so unique, so fundamental to our understanding of Earth, that they must be preserved as wild, untouched sanctuaries. Conservation here means allowing the deep to remain deep, to unfold its mysteries at its own ancient pace. It means supporting the tireless efforts of scientists who, with their sophisticated submersibles and remote instruments, continue to map, observe, and understand this hidden world. Their work is a vital act of listening, of bearing witness, allowing us to build a more complete picture of the trench's inhabitants and the subtle changes they experience. It is through this deep listening that we can truly appreciate the resilience, but also the vulnerability of these deep-sea ecosystems. This protective embrace extends beyond borders, encouraging international cooperation and a shared sense of stewardship for the global ocean. It reminds us that our planet is a single interconnected system, where the health of the deepest trench is ultimately linked to the choices we make on distant shores. It's a gentle reminder that even in our pursuit of progress and discovery, there are places that call for reverence, for stillness, for protection. The Mariana Trench, in its silent grandeur, invites us to consider our place in the world, not as masters of all we survey, but as humble, responsible inhabitants. The Mariana Trench, for all its profound depth, is not a final destination, but merely the first whisper of a much grander story yet to unfold. We've only just dipped our toes, or perhaps our most advanced probes, into its darkest chambers. The true scientific potential, the shimmering promise of discovery that lies beneath those crushing pressures, is as vast and unexplored as the cosmos itself. To truly unlock these secrets, we dream of a new generation of intrepid explorers, not always human, but often their tireless robotic proxies. Imagine autonomous underwater vehicles, or AUVs, like silent, sleek, deep-sea dreamers designed to endure. These aren't just simple submarines, they are highly intelligent machines, built with pressure hulls forged from materials so advanced they can laugh in the face of pressures that would flatten steel like tissue paper. Perhaps they'll be crafted from novel ceramics or even diamond-like carbon composites, allowing them to descend with unprecedented resilience, tirelessly mapping the seabed with multi-beam sonar, sketching contours and features we can only guess at today. These robotic pioneers could linger for weeks, even months, powered by advanced energy sources, sampling the water for faint chemical whispers of undiscovered life, or taking core samples from the very bedrock, revealing millennia of Earth's geological autobiography. The development of these advanced AUVs will revolutionize our understanding. Picture them gliding through the inky blackness, equipped with bioluminescence detectors to spot unseen creatures, or chemical sensors sensitive enough to detect minute plumes from hydrothermal vents, pinpointing new sources of life and energy. High-resolution cameras, specially designed to function in low light, will capture images of organisms and geological formations previously beyond our reach, sending data back through ingenious acoustic communication systems that defy the crushing pressures. These tireless ambassadors of science will allow us to visit the trench not just once every few decades, but continuously, building a vibrant, dynamic picture of its hidden world. Perhaps the most thrilling potential lies in the realm of biology, particularly with the extremophiles, those remarkable organisms that thrive in conditions utterly hostile to most life. We've already glimpsed the existence of piezophiles, pressure-loving bacteria and archaea, and xenophytophores, giant single-celled amoebas that construct elaborate shells. But what else awaits? We suspect there are entire lineages of life adapted in ways we can barely conceive. These organisms are not just curiosities. They are nature's master chemists. Their unique enzymes, proteins designed to function perfectly under immense pressure and often extreme temperatures, hold the potential for groundbreaking biotechnological applications. Think of these enzymes as biological keys, custom-made for the most extreme locks. They could inspire the creation of new, more efficient industrial detergents that work in cold water, or novel drugs that function under conditions previously thought impossible, or even help us process waste more sustainably. The deep ocean, in this sense, is not just a dark abyss, but a sprawling, living, biochemical laboratory, offering solutions we haven't even begun to conceive. Imagine discovering a microbe that can break down plastics efficiently in harsh environments, or an enzyme that catalyzes reactions with extraordinary energy efficiency. The deep-sea microbial communities, thriving by chemosynthesis around vents and seeps, are like tiny engines of novel biochemistry, waiting for us to decipher their secrets. Beyond biology, the Mariana Trench whispers ancient geological tales. It is the birthplace of subduction, the majestic process where one of Earth's colossal tectonic plates dives beneath another, slowly, inexorably, like a sleeping dragon consuming itself. Future exploration will allow us to place more sophisticated sensors directly into these subduction zones, observing their slow, grinding ballet in unprecedented detail. We can learn more about how water is dragged deep into the Earth's mantle, a process that significantly influences global sea levels over geological timescales and even drives volcanic activity far away. Understanding the precise mechanisms of subduction, the deep earthquakes that ripple through the descending plate, and the resulting tremors that shake distant shores could help us better predict and prepare for seismic events. The Mariana Trench is a living textbook of plate tectonics, and we've only read the first few pages. And what of astrobiology? This silent, submerged world offers an astonishing terrestrial analog for environments we suspect exist far beyond our planet. Consider Jupiter's moon Europa, or Saturn's Enceladus, icy shells concealing vast subsurface oceans warmed by internal heat, potentially hosting hydrothermal vents not unlike those found in our own deep seas. By understanding how life thrives in the Mariana Trench, how it adapts to perpetual darkness, immense pressure, and unique chemical gradients, we gain invaluable insights into the fundamental requirements for life itself. The instruments and techniques we refine for exploring Earth's deepest reaches will be directly applicable to future missions to these icy ocean worlds, helping us design the probes that might one day detect extraterrestrial life. The Mariana Trench is, in a profound sense, our local launch pad to the stars, guiding our search for life beyond Earth. The tools and techniques we develop to explore the Mariana Trench, from ultra-pressure-resistant materials to advanced imaging and communication systems that can penetrate kilometers of water, will not only serve oceanographers, they will push the boundaries of engineering, creating spin-off technologies applicable in aerospace, medicine, and countless other fields. The challenge of the deep becomes a crucible for human ingenuity, forging advancements that benefit us all in ways we can only just begin to dream. Imagine medical implants made from materials as resilient as those used in deep-sea vehicles, or sensors so sensitive they can detect the faintest signals within the human body. But as we gaze into this future, a gentle reminder floats to the surface of our minds. The Mariana Trench is not merely a scientific playground. It is a fragile, pristine wilderness, a sanctuary of unique life forms and geological wonders. Future exploration carries with it the profound responsibility of preservation. We must approach this exploration with reverence, ensuring that our quest for knowledge does not disturb the delicate balance of this extraordinary realm. The discovery of microplastics and persistent organic pollutants, even in the deepest parts of the trench, serves as a stark warning and a call for conscientious exploration. It is a vital global ecosystem, playing a role in the planet's vast carbon and nutrient cycles, and its health is inextricably linked to our own. We must allow its secrets to unfold naturally, like a slow-motion blossom in the deep, undisturbed by our hurried intrusions. These silent, futuristic expeditions, sending their data streams back to eager scientists on distant shores, remind us that the Mariana Trench will continue to beckon, a profound mystery at the heart of our own planet. It is a constant invitation to wonder, to learn, and to dream of what lies just beyond the veil of the unknown. And with each gentle wave of scientific curiosity, we draw a little closer to understanding the grand tapestry of life and Earth, one silent, shimmering secret at a time. We have journeyed into the silence, past the crushing weight of water, to the very bottom of our world, the Challenger Deep. But as we rest here, cradled by the soft currents of imagination, let us remember that the Mariana Trench, profound and remote as it is not an isolated wonder. It is a vital, beating pulse within a much grander global system, the deep sea. This vast, largely unexplored realm encompassing over 90% of our planet's living space, holds secrets and functions that resonate through every breath we take, every wave that laps ashore, every cloud that drifts across the sky. Its significance stretches far beyond its hidden canyons and shimmering vents. It is the silent engine, the grand library, and the ancient memory keeper of Earth itself. Imagine, if you will, our entire planet as a vast, living organism, breathing slowly, profoundly. The deep ocean, particularly its abyssal plains and trenches like the Mariana, acts as its most crucial lung and a silent, colossal memory bank. For eons, it has been drawing breath, not of air, but of carbon, an element vital for life, yet, in excess, a warming blanket for our world. Tiny organisms in the sunlit surface waters, busy with photosynthesis, capture carbon from the atmosphere. When their brief lives conclude, they embark on a long, slow journey downwards, a delicate rain of organic matter we call marine snow. Each snowflake, each tiny particle, carries a fragment of that captured carbon. It drifts, sometimes for millennia, through the water column, a solemn procession into the perpetual night. Much of it is consumed by the creatures of the deep, returning to the cycle. But a significant portion, billions upon billions of tons over countless ages, settles. It settles into the fine, silty sediments of the abyssal plains, compacting slowly, becoming part of the Earth's very foundation. These ancient layers of sediment are like pages in a cosmic diary, each recording a moment in our planet's carbon story, holding it captive, preventing it from returning to the atmosphere to intensify the greenhouse effect. The deep sea, in its quiet, consistent work, has been regulating our planet's climate for geological timescales. An unsung hero, a vast, cold vault safeguarding the delicate balance of our atmospheric conditions. Without this profound carbon sink, our world would be a very different, likely much warmer place. It is a slow, patient process unfolding over eons, yet its impact on every breath we take, every temperature fluctuation we experience, is immeasurable. But the deep sea is more than just a climate regulator. It is a sprawling, living museum, a hidden garden of unparalleled biodiversity. In the profound darkness, where sunlight never penetrates, life has evolved in ways that challenge our very understanding of existence. Consider the hydrothermal vents, like those we might find along the mid-ocean ridge or even near the Mariana Trench, where superheated, mineral-rich water spews from the seafloor. Here, life doesn't rely on the sun's energy, but on chemosynthesis, harnessing chemical reactions for sustenance. Giant tube worms, blind shrimp, and bizarre fish thrive in these toxic, scalding environments, forming oases of vibrant life in an otherwise barren expanse. These creatures possess unique biochemical pathways and genetic adaptations that could hold keys to new medicines, resilient materials, or entirely new understandings of how life can flourish under extreme conditions. Every year, new species are discovered in the deep, each a testament to the planet's boundless inventiveness. It's like finding new chapters in an ancient, forgotten book, each revealing a wonder we never imagined. The genetic library of the deep sea is vast and largely uncatalogued, a treasure trove of potential innovation waiting patiently in the dark, reminding us that life's tapestry is far richer and more intricate than we often perceive from our sunlit shores. Beyond the carbon and the creatures, the deep ocean participates tirelessly in the Earth's grand nutrient cycles. Marine snow carries not just carbon, but vital nutrients like nitrogen and phosphorus from the surface down into the depths. This downward flow sustains the myriad of life forms that call the deep their home, preventing these essential elements from becoming locked away forever at the bottom. Meanwhile, upwelling currents in other parts of the ocean bring nutrient-rich waters from the deep back towards the surface, fertilizing productive fishing grounds and supporting surface ecosystems. It's a vast global conveyor belt, an unseen circulatory system that keeps the entire marine world humming with activity, a constant exchange that connects the sunlit shallows to the crushing abyss. The microbes of the deep, too small to see but immensely powerful, act as the unseen choreographers of these cycles, breaking down organic matter and recycling nutrients with an efficiency that beggars belief, influencing the very chemistry of the oceans and, by extension, the planet. And let us not forget the deep sea's foundational role in the very making of our planet. The Mariana Trench itself is a dramatic testament to the slow, powerful dance of plate tectonics. It marks a subduction zone where one massive oceanic plate dives beneath another, returning old crust to the Earth's fiery mantle. This process recycles planetary material, drives volcanism, forms mountains, and generates earthquakes, constantly reshaping the Earth's surface. Hydrothermal vents, with their mineral-rich plumes, are born from the spreading centers of these plates, creating new seafloor and enriching ocean waters with vital elements. The deep sea floor is a dynamic canvas where geological forces play out on timescales beyond human comprehension, revealing the raw power that sculpted our continents and continues to define the very architecture of our world. It reminds us that our planet is not static, but a living, breathing entity with its deepest parts playing an active role in its ongoing transformation. So, as you drift deeper into peaceful slumber, remember that the seemingly distant, desolate deep sea, a realm of perpetual night and immense pressure, is in fact intimately connected to every aspect of life on Earth. It regulates our climate, hosts an unparalleled diversity of life, orchestrates essential nutrient cycles, and actively sculpts our planet's geology. Its quiet work unfolds far from our everyday gaze, yet its influence permeates everything. It is a global engine, a silent guardian, a profound mystery still largely unraveled. And as we dream, we might ponder the many more wonders and vital lessons that this vast, dark ocean still holds, waiting patiently to be discovered, waiting to teach us more about our extraordinary planet, and perhaps about ourselves. Tomorrow, as the first light touches the horizon, we might explore some of the specific creatures that have adapted to these incredible conditions, their unique strategies for survival in a world without sun. But for now, let these thoughts gently carry you further into the quiet of the night. Our gentle journey, a quiet descent into the heart of our blue planet, now softly concludes. We embarked together on an imagined voyage to a place so profound, so distant from the sunlit world, that it whispers tales of ancient Earth and secrets held for eons. We spoke of Mariana not just as a location on a map, but as a feeling, a deep breath taken by the Earth itself. Remember the soft beginnings of our descent, a subtle slipping away from the familiar surface. The light, once bright and dancing, began its slow, graceful fade. It wasn't a sudden plunge into blackness, but a gradual velvet curtain drawing across the scene, tinting the waters with deeper and deeper shades of indigo, then sapphire, and finally a profound, all-encompassing inkiness. This deepening wasn't frightening. Instead, it was a gentle invitation to let go, to trust the quiet envelopment of the ocean's embrace. We felt the world outside our cozy bubble transform, becoming less about the bustling, vibrant tapestry of the shallow seas and more about a singular, breathtaking stillness. With each imagined fathom, the sounds of the surface world, the crashing waves, the calls of birds, the distant hum of human endeavor, receded, growing fainter and fainter, until they were no more than a phantom echo. In their place, a different kind of sound emerged, the sound of quiet itself, a quiet so pure, so absolute, that it resonated not with an absence of noise, but with the subtle, profound heartbeat of the deep. It was the hush of immense water, the softest rustle of unseen currents, the almost imperceptible whisper of existence in a realm untouched by our daytime world. This quiet became a gentle companion, a soothing presence that invited introspection and a deep sense of peace. We imagined the gradual transformation of the landscape, from the vibrant coral gardens near the surface to the vast, undulating plains of the abyss. Then, further still, to the truly unique, sculpted terrain of the trench itself, not a place of harsh edges and jagged peaks, but a realm shaped by immense forces over unimaginable stretches of time, yet smoothed by the eternal flow of the deep. It was a place where beauty took on a different form, a stark, elegant, and humbling grandeur. The very ground beneath us, we imagined, was woven from the dust of ages, a gentle carpet of history, silent and undisturbed. And the life we encountered, or perhaps simply sensed in our quiet journey, was a testament to enduring wonder. These were not creatures of hurried existence, but patient, resilient beings, perfectly attuned to their profound home. Their presence, whether glimpsed or simply felt, added another layer to the deep's gentle mystery. They were a reminder that even in the most extreme, most secluded corners of our world, life finds a way to blossom, to adapt, to thrive with a quiet determination that is deeply inspiring. Their existence is a soft reassurance that the earth, in all its vastness, holds countless secrets, countless forms of beauty beyond our easy comprehension. Our journey to Mariana, then, was not just about the incredible depth, but about the quality of that depth. It was about discovering a place where time seems to slow, where the hurried pace of the surface world dissolves into an ancient rhythm. It was a journey into a realm of profound stillness, where the earth holds its breath, allowing us to feel the quiet immensity of creation. It asked us to reflect on the sheer magnificence of our home planet, to ponder the mysteries that lie beneath the shimmering veil of the ocean, and to appreciate the delicate balance of life in all its myriad forms. This gentle descent into Mariana has been an invitation to peace, a soft lullaby sung by the earth itself. It has shown us that even in the deepest, darkest parts of our world, there is an enduring serenity, a quiet resilience, and an ancient, gentle wisdom. As we now prepare to drift into our own slumber, let the profound calm of Mariana settle over you. Feel the quiet stillness, the gentle envelopment, the reassuring darkness of that deep, wondrous place. Let the echoes of our journey gently guide you. The mystery and wonder of Mariana, like a soft current, will continue to flow through your thoughts as you close your eyes. For even as you rest, your mind, like the ceaseless ocean, will continue its own gentle explorations. The journey, dear friend, does not truly end here. It simply transitions, peacefully, beautifully, into the quiet, boundless oceans of your dreams. Sleep well, knowing the world holds such deep, calming wonders, and that a piece of that quiet wonder now rests gently within you. Good night.